Up to now, we have treated charges mostly as isolated points or continuous distributions. Today, we study the dipole, the simplest non-trivial arrangement of charges, the building block of molecules, matter, and modern physics. An electric dipole consists of two-point charges, plus q and minus q, separated by a small distance 2a. The dipole moment, p vector, is defined as q times 2a d hat, where d hat is a unit vector from minus q to plus q. A dipole is not just about two charges. It is about a directional property of space created by those charges. The physical meaning of the dipole moment includes its magnitude, which indicates how strong the dipole is, and its direction, which shows the orientation of the dipole in space. Real-world examples include the water molecule, H2O, which is a dipole, and dipole interactions are crucial in proteins, acids, salts, and insulators. For JEE, many questions hide a dipole inside a complicated diagram. Identify it quickly. Now, we calculate the electric fields due to a dipole at two special positions. First, the field on the axial line, along the dipole axis. The result for the electric field on the axial line, E axial, is 1 over 4 pi epsilon naught times 2p over a cubed. The direction of E axial is the same as the dipole moment vector, p vector. Note that the axial field is stronger than the equatorial field. Second, the field on the equatorial line. The result for the electric field on the equatorial line, E equatorial, is 1 over 4 pi epsilon naught times p over a cubed. The direction of E equatorial is opposite to the dipole moment vector, p vector. In both expressions, the denominator is r cubed. This tells you something profound. Dipole fields decay faster than monopole fields, which decay as 1 over r squared. This is why dipoles dominate only at short distances and determine molecular interactions. Next, let's consider the torque on a dipole in a uniform electric field. A dipole placed in a uniform field E experiences a torque but no net force. The torque, tau vector, is given by p vector cross E vector. The magnitude of the torque, tau, is p e sine theta, where theta is the angle between p and E. Physically, the field tries to align the dipole to minimize energy. There is no net force because equal and opposite forces on the charges cancel out. Now, the potential energy of a dipole in a uniform field, U, is minus p vector dot E vector, which equals minus p e cosine theta. Interpretation: minimum energy occurs when theta is 0 degrees, meaning the dipole is aligned. Maximum energy occurs when theta is 180 degrees, meaning it is anti-aligned. JEE trap: if a dipole is released from rest at an angle, its potential energy converts to rotational kinetic energy. For advanced JEE, consider a dipole in a non-uniform electric field. In this case, the dipole experiences both a net force and a net torque. This is because the forces on plus q and minus q are unequal. An important result for the force, F vector, is p vector dot del operator acting on E vector. Nature pulls the dipole towards the region where the electric field is stronger. This explains why neutral objects get attracted to charges through polarization, creating a temporary dipole. Next, the work done in rotating a dipole from an initial angle theta 1 to a final angle theta 2 is W equals P E times cosine theta 1 minus cosine theta 2. This is a very common JEE question. Given an angle, compute work, or given work, find the final orientation. Finally, let's look at the general field at an arbitrary point. The general field in vector form, E vector, is 1 over 4 pi epsilon naught r cubed times 3 times p vector, r hat times r hat minus p vector. This single formula reproduces both axial and equatorial results. It is advanced but beautiful. Common JEE mistakes include using dipole formulas when r is not much greater than a, forgetting that the equatorial field is opposite to the dipole moment, and mixing torque and force concepts. Also, writing P equals QA instead of P equals 2AQ, and forgetting the direction of torque are frequent errors. A dipole placed at 60 degrees to the electric field. Work done in rotating it to 0 degrees. Use the formula W equals P E times cosine 60 degrees minus 1. In a uniform field, torque exists, but force does not. The correct reason is that forces cancel, but torques add. At the same distance from the dipole The ratio of E axial to E equatorial is 2. Two equilibrium positions exist. Theta equals 0 degrees is stable, and theta equals 180 degrees is unstable. Understanding the energy curve is key. The dipole seems simple, but it governs everything from atoms to galaxies. Master this, and the rest of electrostatics becomes beautifully predictable.